Let's see anything. Oh, that's when Robert comes up. Yes. How many do we have line signed in, Kimberly?
There are 86, 89, 91,
Yeah. So I'll just say
102.
a quick good afternoon. Welcome, folks. As you're probably aware, on webinars, it's customary to leave a couple of minutes for people to wander in. It's sort of eerily similar to when we used to have in-person meetings. Robert, back in the day, we used to give people a few minutes to grab one more donut before we started the session.
Right.
No donuts in this case, but we'll still give people a couple minutes to settle in,
Yeah. Probably a good thing. I think those things are sleeping pills.
I guess. I feel bad for Tim Horton, I just feel like we should still just,
Well, I guess if you have coffee and a donut, they kind of cancel each other out, right?
there you go.
So,
There you go. I took donuts to a meeting recently and maybe a dozen, and I took back home 9 out of the dozen. Nobody's eating donuts. It's to your point. I guess everybody's doing a better job.
yeah.
So again, we'll give people just a couple of seconds. Just welcome you all to our webinar series, the Critical Canadian Building Science webinar series, hosted by Building Knowledge Canada, and almost always sponsored by Enbridge, which we're always pleased. And this particular session is co-sponsored by CASE, the Canadian Association of Consulting Energy Advisors, and you'll hear from Representative from CASE in just a minute. This particular segment, if you weren't on day one, you missed, that was Monday, you missed just a great session. I know we had some great comments from folks who were on day one. I think there was over 200 signed in, so that was great. So we'll just wait a couple more minutes. But it's very exciting for us to have Robert Bean. We're just so thankful, frankly, that Robert would spend 2 afternoons, well, I guess 2 mornings in your case, Robert, being
Yeah.
with us.
Yeah.
And you said something about you need to finish right on time because you're heading out to backcountry. Well, not quite right on time, but you're
We
heading.
are. We're taking my granddaughter and son out to the mountains for the weekend. So it's a multi-day trip.
That's great. How old
Yeah.
granddaughter?
She's 5.
Beautiful. Oh, you love
Yeah.
that. So thank
Yeah.
you. Good. Well, I do think, given we've got an aggressive agenda, I do think we'll get started. And I'll say again, welcome. My name is Gord Cooke with Building Knowledge Canada. Welcome to yet another in the series of the Critical Canadian Building Science webinar series. This specific one is a two-parter. This is the second part, Designing for People, Thermal Comfort Principles and Practical Applications for Residential Homes and Buildings. So we have you for about an hour and a half. We will have time for questions. Somebody immediately and I always ask, can we get a copy of the presentation? And the answer is yes. And then I'll remind you, this is content that Robert has curated and accumulated over a career. So if, in
Yeah.
fact, when you use the information, Robert, they should use it wisely and they should use it with accreditation. Is that a fair?
Yeah, that's right. The presentation in its entirety is copywritten, but if you want to use one or two slides, all I ask is you ask for permission. And some of the content has been created by others. So I don't own the copyrights for those, so you'll have to reach out to those people. Yeah.
What a nice statement so you're giving them free access to view and learn from. If they
Yeah.
want to, they can't use the whole presentation, but if they'd like to use a slide or two, then just reach out, ask for
Absolutely.
permission.
Yeah. Yeah, you
And
bet.
what a very generous offer. Really appreciate that. Thank you.
Yeah.
And there it is there. I want to use this slide just to say thank you to our sponsors. And I'll actually we have online Brandon from Enbridge who would like to just share a few things with you. So I'm going to stop sharing and allow Brandon to share his screen. Good
Yeah, it
afternoon,
should come
Brandon.
up in a second there. Can you just give me the thumbs up that we're
Yep, we're there.
able to see it?
Thank you. You're
There
there.
we go. All right. Hello, everyone. It's a pleasure to be part of these building knowledge webinars. My name is Brandon Leithart, and I'm an advisor for residential new construction HVAC accounts on our strategic accounts team. We like to start off every session with a land acknowledgement. Oh, there we go. So yeah, just acknowledging that the land on which we gather is the traditional and historical lands of the original people of Turtle Island, who have been the caretakers of these lands since time immemorial. Today, this gathering place is home to many First Nation, Métis, and Inuit peoples. Our acknowledgement of this reminds us that our great standard of living is directly related to the resources of and relationship to Indigenous people, and we have a responsibility to honor that.
And Brandon, I would just mention, I just recently was down in New Brunswick for the, was it Nova Scotia? Sorry, Nova Scotia for the First Nations building officials conference. And it's always a fascinating conference to see First Nations group from across the country doing the same kinds of things you and I do, which is try to help build people build better houses. I was reminded of their oral history that dates back about 600 generations. That is, I know my
Yeah.
family, I can trace back 4 or 5 generations to when they came to Canada. The First Nations groups have been here 600 generations. I just think that's an amazing stat. So I just wanted to mention that because I just came back from that conference. So thank you for that. Sorry, go ahead, Brandon.
Yeah, thanks for sharing, Gord. 600 generations, that's almost
That's crazy.
incomprehensible. But yeah, on the topic of backcountry, we have a TikTok here. Just a couple quick reminders. They seem to be becoming more and more common. I was just at an event last Thursday. It was the West End HBA golf tournament, and we sat down for dinner, and one of my coworkers was sitting beside me, and we were talking about ticks, and he kind of looked down at his legs, and lo and behold, there was one crawling on his legs. So,
Wow.
yeah, just knowing the risk areas, forest, tall grass, especially in kind of brushy areas, wearing long sleeves and pants, and especially if you can tuck them in, even tucking your pants into your socks. I know sometimes it gets hot, but if you have the ability to do that, that's one way to help protect yourself. Obviously, using bug repellent, and then becoming familiar with what their appearance is. I think for me, the first time I noticed a tick on me was last year, and that kind of led me down the rabbit hole of learning all the different types and what the different tick-borne illnesses that they carry. And the Lone Star tick with the red meat allergy definitely scared me a little bit. But I learned a lot through that, and now I'm able to identify them. So checking yourself often, especially when you've been outside, and then acting quickly if you've been bitten. If you have been bitten, removing it with tweezers or kind of pinching it with your fingernails is important. But usually if you catch it within 12 hours, I think the risk is quite low. It's once you start getting, once the tick's been on you longer, that's when the risk increases. So just a reminder to everyone to take that few seconds to do a quick check after you've been outside. And then one of the things that I've been working on at Enbridge is putting together this HVAC newsletter. The plan is kind of to roll it out once every quarter, and it has things like tips and advice that are all related to natural gas, the meter clearance summary, and a load and pressure change guide were features on the Q1 newsletter. The Intellis meter guide is they're the new meters with the image on the right here. I've had a lot of questions on them, and so we've got an updated kind of info guide coming out for those. And then also just things like timely reminders, and when we get updates for online tools, one of them being the safety violation tool. So you can go on, submit infractions, clear them, and it makes it a lot easier to kind of track them. This safety violation tool, they're making there's ongoing improvements to it. So I think right now there's already been improvements. By the end of the year, there'll be some much better improvements. I'll just say that. So yeah, the links down here, it's pretty simple, enbridgegas.com/HVAC support. And that image there is kind of what the web page looks like when you pull it up. And with that, I'll hand it over to Gord. Stop sharing
It's
here.
always interesting to me as we just transition here, that, Enbridge has been, from my perspective, just a really good industry partner. Sometimes people ask us, why is Enbridge part of this kind of work? And I would say because they understand the industry. They've always been good, responsible partners in the industry, and frankly, helping people use less of the product that they sell, right? That understanding that the wise and safe use of natural gas is where we need to be, and then looking to reduce our dependence on fossil fuels. Enbridge has been very supportive of that message. So thank you, Brenna, for sponsoring yet again. And then we have Gilles Lesage from representing Casey in this case, the Canadian Association of Consulting Energy Advisors. Welcome, Gilles, and just give us a few words.
Absolutely. Thank you, Gord and team. Yes, I'm Gilles. I'm here in BC at the moment, here to represent our KC, Canadian Association of Consulting Energy Advisors. I am an energy advisor, but my other kind of capacity is the technical liaison director for KC. So we are so happy to be here and supporting initiatives and sessions just like this, because our goal in the end is to elevate the energy advisor profession. We're about 11 years old right now. We started back in 2015, where I was fortunate to be one of the founding members. And we had a very small numbers, and fast forward 11 years, and we've got about 300 across the country. So, and we're having conversations, very important ones, with industry all across the country. So with that said, very happy to be here. Our members are always like to kind of go down the rabbit hole and nerd out on or some sessions just like this one. So, and I had the pleasure of seeing some of this presentation at Spring Camp a few months ago, which has always been great. So always a great presentation, and looking forward to part two.
Thanks, Jill, and thanks for that plug for Building Knowledge Spring Training Camp. Those who don't know of it, it's a fun a 2-day seminar, workshop, let's call it conference, I guess some would say, just north of Toronto. And we're always happy to host and have great speakers like Robert give us their sense of what's happening in the industry. So thank you for that. We could also imagine that KC members could indeed be the folks who might implement some of the design things that we're going to be talking about today. So I'll challenge those on the call who are energy advisors to take note. There is training that's available to be better at or to be competent in doing comfort design work. So that's pretty useful. Thank you for that. And Kimberly, I don't know, because it's a two-parter, whether we need to run the polls again. What are your thoughts? Should we figure out where people are from?
Up to you and Robert. Yep.
Robert, how you feeling? Do we want to just continue on?
Let's just continue on.
Fair enough. I know we've already cut into some of your day at time. I wanted to start with, for those who were on day one, I just wanted to highlight a couple of things that I personally took away. One, on the left-hand side there, Robert showed all kinds of examples of how humans literally over centuries have been trying to struggle with comfort in their own climate. Things like natural draft, convection loops to cool off in very hot climates. Second, so there's a lot of history. Two, comfort is subjective. I heard that loud and strong. We're not allowed to tell people we're going to make them comfortable, because that's up to them to decide. It's inappropriate of us to say, of course you're going to be comfortable, or to make claims about comfort, because it is subjective, and we're going to chat about that more. Three, I thought one of the most fascinating, and I've felt it for a while, is this idea that we've boiled down our responsibility to meeting a number. And the number, unfortunately, is not a comfort metric at all. It's an equipment metric at best, and it's sensing itself. I love that. It's sensing itself. It's not sensing what humans are actually experiencing or feeling. Yeah. And then, Robert, today, I think you're going to take us into the standards and the tools that are here to help. That is, we don't need to despair, that there are things that we can do in our daily lives, both new and existing housing, to create comfort conditions, that is, conditions for comfort. And you school this wisely. Don't say it's going to be comfortable. but
Yeah.
let's talk about designing so that we can create conditions that people may find comfortable. Is that a fair way of saying it?
That's a great way of saying it. You bet.
Great. So at that, I'm going to stop sharing. That was sort of the learning. I will remind folks as you pull yours up that we will have time for Q&A. We're happy to hear and see folks put things in the chat. If you have a question that you want answered specifically, it's better to put in the Q&A. I think people understand that there's a chat and there's a Q&A function. Q&A is we're able to capture that better and actually create responses to it. So I'll encourage you to do that. And off to you, Robert.
All right. Thank you, Gord, and everybody else. And yeah, another acknowledgement to our sponsors. Obviously, this type of education program doesn't happen without support. And it's been great to be an invited guest of Building Knowledge Canada over the years, actually, in all of these programs that we've done. And I think we're making progress, Gord. I don't know about you, but I love seeing people come back to spring camp and talk about what they're learning. And that last program that we did in the spring of this year, like I said, I'm still smiling. I just thought it was a huge success. So congrats to the team. And then also to Casey and Enbridge for, again, the support is highly needed, and we are making progress. So that's great.
We'll get you to put it into slideshow mode if you wouldn't mind.
Yeah, you bet. Let's see. See if I can do this. All right. Good to go?
There you have it. Thank you.
All right. Yeah, so the next slide here, really what we're going to do is, I'm just going to minimize this screen here so I can look at some content. Kimberly, do you know how I can get, maybe there we go. Is that, whoops. Just hang on a second. What I'm trying to do is to get the screen on the right to disappear. I don't even know if that's possible. Is it?
We don't see a screen on the right. We just see the blue slide
We just see your
with the
blue,
home.
and then we see your picture up top. So,
well, I'll tell you what, we'll try to I'm not sure why that is, but I might, well, let's just take it and see where we go. Anyways, one of the very first things that we need to talk about today. So as Gord gave us a quick summary, today what we're going to do is talk about how you see spaces and people through the lens of the thermal comfort assessor. And what we want to make sure is that first and foremost, we recognize that there are different people occupying spaces. Not everybody is the same. And as a result of that, whoops, hang on a second here. Sorry about this. As a result of that, we don't want to make assumptions that everybody is the same. So who are we actually designing for? And that is really important, particularly when you get into multiple families living at home or multi-story, multi-family buildings. So let's start asking questions first. Who are we designing for? And as we learned in part one, we're not designing for the space, and we're not designing for the room. We're not designing for the mechanical systems. We're in fact designing for people. And so we need to start asking some really good questions like, well, okay, so who are we designing for? And what are they going to be doing? And what are they going to be wearing?
and tragically, we heard we should have been designing for the person with the gun, the person who was so upset about the thermostat setting. We should have understood. Ooh, they've got a gun. We better design for them. Yes.
It was funny. So for those who were in the first presentation, yeah, we brought up that. But then Gord, afterwards, I was thinking like we were talking about perspective, and we showed slides about thermal comfort standards for cattle and poultry and rodents and pigs. And I thought, well, what happens if cows had guns?
Yeah.
What would that barnyard look like? So anyways, and then when we start to talk about the metrics, and we kind of introduced them in the first part, when we talk about air temperature, it's really important to understand that what we're talking about is not what the thermostat is reading, but in fact, what is the air temperature around the person? And we make this statement that where the person goes, so goes their sense of comfort. They carry it with them, and it's not represented by anything other than their own bodies and their own minds. And then we talked about mean radiant, and we mentioned that several times, and we're going to talk about that quite a bit in the next hour and a half or so, or hour 15 minutes. But this term represents all of the surface temperatures around us. And why it's incredibly important is that roughly 60% of the sensible heat transfer that people have with their environment is via radiation. It's not convection, it's not conduction, it's not evaporation, it's in fact radiation. And so because it plays such an important role, we need to pay attention to these surface temperatures around us. And if you think back in your careers about the evolution of energy efficiency in buildings, all buildings, housing, commercial buildings, institutional buildings, and this importance of improving the enclosure, well, what the consequences of improving enclosure is actually now we're starting to manage inside surface temperatures. So those two are related. And so let's not forget about that. And we've all experienced that. Like when you think about, standing next to a large pane of glass at minus 40 degrees, it's not pleasant. But if you go into the interior of the space, your perspective or the change, what you sense and what you perceive changes as well. So let's keep that in mind. And then the next thing we want to talk about is air velocity. So what is the air velocity around the person? Again, this isn't what the velocity is coming out of the duct. So when you're doing your load calculations, if you're doing air-based systems and you're looking at the diffusers that you're using or registers, and there's these terms, throw, drop, and spread. We're not talking about any of that. We're actually talking about what is the air velocity around the person. And that'll come really important here in the next few slides. We also want to talk about relative humidity. And they say it's relative, right? Because it's related to the dry bulb temperature. Well, what do we know about dry bulb temperatures in buildings? We know it's not homogeneous. We start to approach the exterior of the building, and particularly here in extreme climates, that temperature is going to drop, and that's going to change the relative humidity. So RH is important, but as you're going to learn here throughout the next while, is that humidity, although we recognize it as having a role, in particular in hot, humid climates, there are ways that we can compensate for elevated humidity. In fact, in the standards, we actually don't have limits. There are limits for building science purposes, there's limits for indoor air quality purposes, but when it comes to thermal comfort, we can actually drive humidities up and down, even though it might have consequences elsewhere. Then we also look at what happens to people when they're in a low MET activity and wearing low clothing. There's other factors that come into play. We want to know what are the temperature profiles on either side of the person. We call that radiant asymmetry. We want to know what the temperature stratification is. That is the difference of temperature between the dry bulb temperature, between their ankles and their head. We want to know what the drafts could be in that space. Ankle drafts in particular are really annoying, especially in, again, cold climates where you've got this change in density as the air hits that glass, changes the profile characteristics of it, starts to come down the glass, and now you've got this draft. So we want to know about these things because they will also play an influence on people's perception. And then also elevated air speeds. And elevated air speeds actually work really well in hot climates, hot, humid climates. We don't want to be doing this during the wintertime, but there's lots of times where we can actually use mechanically induced elevated air speeds as a way to provide the sensation of cooling. Not that we're actually cooling the space, because we're not actually changing the air temperature, but we are elevating the airspeed, which improves the cooling off of the occupant. And so there was a big push within our community at ASHRAE, SSPC 55, our committee that deals with this stuff, to rather than use more mechanical refrigeration, to look at using elevated air speeds as an alternative way to providing the sensation, the perceptions of cooling. So one of the conclusions we have here going into the next part of this presentation is that thermostats do not sense what people sense. They sense themselves. They're not located where people are in the space. They don't recognize all of the metrics. And even if you say, well, they do recognize air temperature, yes, that is a true statement, at the place where they're located. They don't represent the air temperature where the person is located. So we really want to be careful of that. And when we talk about thermal comfort, we oftentimes hear people say, well, it's a gender issue. It's males versus females. And we've seen that all over the world. And part of that has to do with research that was done that was flawed. The big publication houses, the Wall Street Journal, the New York Times, they all pick up this stuff and then they distribute it without actually digging into the source. And so when you dig into the source, you find that for the most part, genders have very similar physiological systems in terms of the sensing and perception of thermal comfort. There are some differences, but it's more of an academic interest. What really drives discomfort between the genders has a lot to do with clothing, the restrictions on the ability to adapt. But at the very core of it all sits architecture, enclosure, interior systems. When these passive systems have flaws in them, and we try to compensate for them with mechanical systems, this is where one of the big problems occurs. And when it comes to mechanical systems, oftentimes we're trying to solve a problem that we actually don't quite understand it, and we're using HVAC systems that may not be matched to the problem. So we say when we have a radiant problem, we solve it with a radiant solution. When we have a convective problem, we solve it with a convective solution. Don't mix those two up, which we have done for many, many generations, and that has led to a lot of problems inside spaces. So when we talk about thermal discomfort and thermostat wars, we have to understand it actually always starts with the architecture when we're talking about design. Then we look at the enclosure, then we look at the interior systems, and then we look at HVAC, matching the solution with the problem, and then also pay honor to the diversity of people occupying the spaces, that some people are going to have different needs than others, and if you can design for that, great. If you can't, then give them the ability to adapt with other means. So that's really important in this next part of this presentation. So if we really want to create these conditions, and Gord, thank you for bringing that up in your slide about the importance of the wording that we use is really important, then we can create conditions. And so let's talk about the conditions that are these discussions that we need to have with our clients. So on the left-hand side are the basic ingredients of the thermal comfort cake. And I would suggest to you, again, if you're using air temperature as a proxy for thermal comfort, that's like calling baking soda a cake. You're missing everything else in the process. So we use all of the ingredients to evaluate it, and we need to sit down with our clients through those lenses and say, okay, who are we designing for? What are the special needs that might exist? And we need to understand that thermal comfort is not an actual condition of the space, but in fact, what's actually going on in the mind. And we showed slides in the first part about positron emission tomography. You can actually see the brain lighting up as you change the environment around it. So let's make sure we understand that. And everybody's brain is not the same. So it's subjective, as Gord brought up the point that everybody is different. Not everybody's going to sense the space in the same way. So we're sitting down with the client and we're looking at maybe the draft form of a set of drawings, and we want to talk about how does seasonal changes affect the indoor spaces, and how does as the sun moves across that building, how is the building orientated on the property? What is the architecture, the form, the geometry? All of these things are important because they start to affect this mean radiant temperature, radiant asymmetry, stratification. All of these things come into play. So then, as we're dealing with these design elements, looking at glass, and we're going to talk quite a bit about the importance of the fenestration systems, the amount of window to wall ratios, the performance of the glass, the orientation of the building with glass to the sun. All of these things come into play because ultimately they will affect the amount of energy that comes into the building and how that energy moves through the space. One of the things, and this always, Gordon, maybe you've experienced this in your own presentations, that a lot of people, when they do load calculations, they don't equate the inside surface temperature of glass at heating conditions or cooling conditions and the extremes that they can get. You know, even high performance glass can have these extreme temperatures. So if you think about a really large window to wall ratio, it might be 100% or 80% window to wall ratio. What we want you to start to look at that is as surface temperatures that could easily hit 100 degrees Fahrenheit or 55 degrees Fahrenheit. So here you are, your perception of thermal comfort is to maintain a 20-degree air temperature. In fact, you could have surfaces around you that are way off base, right? And those will drive the expectation. So that's why we say air temperature isn't a proxy for thermal comfort. It requires all of these other metrics. So windows, fenestration performance is really, really important. So when we talk about window to wall ratios and what the client wants to do and what the architect wants to do in serving that client is if we can't get them to back down or be a little bit more conservative with their choice in glass, then to start talking about solar control. And I don't mean on the inside of the building because that's the worst place for it, is to do it on the outside. Develops shading strategies that prevent that shortwave radiation from landing on the building in the first place or coming through the glass in the second place. And I just came back from Brisbane. We were there for a couple of months, and I can't think of any other city in the world that I've been to where they have mastered the art of exterior shading in all building forms, all building shapes. They really understand that, that sun provides wonderful things for humanity, but ultimately, it is, as it's starting to prove out with climate changes of consequence, being a real problem for us inside spaces. So that's really important. And then when you start to talk about the glass, learn about, Gord, I think you probably agree with this. If there's one thing that people could understand in the world of architecture, building science, mechanical design, is to learn about glass, learn about windows, learn about the coatings that you can put on, learn about when you need to go from a double pane to a triple pane. Like all of these things are incredibly important. And I would say that if I was the master of the universe in education programs, I would say that would be one of the key courses I would have people take. Gord, would you agree with that?
I absolutely would agree. And to your point that, energy programs like Hot 2000 for years have kind of like high solar gain glass because it gets you lots of winter free heat from the sun, but it didn't really anticipate the thermal comfort issues that it causes. So yes, I'm getting free heat, but it's too much heat. And what do I do with that? It's causing discomfort. So the more we can learn about glass, even when I say to my clients, our clients, every window manufacturer, Geldman and others, they have 4 to 6 coatings that they can get you, each with, within a really nice realm of cost, similar cost. They can get you 4 to 6 different coatings that could dramatically impact. And I think you're going to show some examples of thermal comfort.
Yeah, you bet. So that's really important. And then we want to talk about, the concept of this. And not many people on the residential side know about Air Distribution Performance Index or ADPI, but we can use these principles to make sure that we have really good mixed temperatures within the space if we're using air-based systems. But we also want to, again, draw attention to the fact that as we go from the inside to the outside, that our relative humidity will change as it approaches colder surfaces. So we want to try to avoid non-uniform areas, and we can do that by using good design practice. And Gord, I think you've been teaching that for a long, long time. So that's important. We want to talk about, particularly in the hot, humid climates, because we do have some people from hot, humid climates. And by the way, again, shout out to those who are from around the world. Again, we have people from India and Egypt and other parts. So thank you for that.
And Ajax, India, Egypt, and Ajax. Thank you.
Yeah, that's awesome.
I'm kidding a little bit. That was nice of Pradeep to say where he's from.
Yeah, exactly. So, and then we want people to understand that when we're talking about these hot, humid climates, that the ability for the body to release energy via the latent process requires that we lower or create a differential between the vapor pressures in the room compared to what's on your skin. And so in other words, if the vapor pressure in the room is the same as your skin, you're not going anywhere with that. So why we dehumidify a space is to create that differential so that if you get into a place where it's overheated and where humidity is playing a role, that we actually enable the body to do that discharge. And we do that by lowering the vapor pressure in the room, which is what dehumidification does. But we're going to talk about that later, about when that becomes important and when it isn't important. All right. We've already mentioned using elevated air speeds in lieu of mechanical cooling. So again, when you're sitting down with your clients, and if they're not willing to, budge on window to wall ratios, or they're not wanting to put on exterior insulation or to solve these thermal problems, rather than going to mechanical cooling as your sort of the default, ask them, just say, well, would you consider using ceiling fans, for example? Some people are okay with ceiling fans. Other people find it unattractive. So, but have that dialogue so that you're not making assumptions about what they like and what they don't like. And then understanding in terms of temperatures radiant solutions for radiant problems, convective solutions for convective problems, and just make sure that we're not trying to solve a problem with the wrong solution, which we have. Unfortunately, we're all guilty of doing that, but it's just keep that in the back of your mind, okay? And then one of the things that's really important when we talk about thermal comfort is there going to be spaces in homes or buildings where people just don't spend any time. And we don't really need to concern ourselves with that. The standard says that if someone's in the space for more than 15 minutes, well, then we need to pay attention to it, right? But if they're not in the space for more than 15 minutes, you know what? Not an issue, right? So we don't worry about boiler rooms. We don't worry about storage rooms. We don't worry about closets. These aren't the things that we're concerned about. We're concerned about where people are actually going to be living and doing the things that they do during the day or night. All right. So then we also want to talk about adaptive comfort, natural ventilation, these types of things. And I'm all for using adaptive methods whenever we can, but we can't do it without understanding that there are risks. So when you think about the drive to use natural ventilation, for example, we're going to open up the inside to the outside. As soon as we do that, we're inviting the outside in. Well, let's define the outside. So the outside can have bad air quality. There could be noise. There could be security issues. There could be protests. There could be all these things that can happen on the outside. As soon as we open up to naturally ventilate our spaces or adapt for comfort, we're inviting the outside in. And that's great if it's got great air outside, there's no noise, there's no security issues, moisture's not a problem. And what I would just challenge you today, and we've been working with other organizations around the world, is that when you push adaptive processes, natural ventilation, natural heating and cooling, that you recognize that every building is on a continuum, as is the community around it. So that you might think that that building today is a good candidate for adaptive measures, natural ventilation, but also try to understand that over the next 50 years, 100 years, anything could come around that building. It could be a meat packing plant, could be a set of train tracks, it could be, you know, a bus route gets put in place next to you, right? So just keep that in mind when you're thinking about using adaptive methods, measures in your analysis. So the hierarchy of design always starts with architecture, the shape of the building, the form, how it's situated on the property itself. The property is important. What's next to the building, the colors that are on the building all come into play. What we call the thermal optical properties, its absorptivity, its emissivity, all of these things are important. Then we look at the enclosure. Now we're talking about the performance of the glass. We're talking about, you know, infiltration, thermal bridging, all of these terms that we use to describe the performance of the enclosure, that comes into play. And then we talk about interior systems. And when I talk about interior systems, I want to make sure that we're not confusing interior design with interior decoration. I made that mistake once while riding from the airport with the senior president of the American Society of Interior Designers. I said, well, what do decorators do? She just about kicked me out of the taxi. So interior designers are people who very much understand colors, absorptivity, emissivity, fire escape plans, all of these things that are important. So interior systems, we talk about placement of furniture, things that might disrupt flow patterns, might affect the thermal comfort of people. They're a big part of it. And then, and only then, do we talk about mechanical systems. So those first three, architecture, enclosure, interior systems, those are all passive solutions. And when they're done right, then it's easy. The mechanical stuff actually gets pretty easy. It's when they have flaws that now we have to do our song and dance on the HVAC side to compensate for their shortcomings. So I always believe that when we look at HVAC, it really is the cleanup crew. If anybody's a fan of John Wick, you all know about the cleanup crew, and that's what HVAC does. It basically says, okay, well, we've looked at all of these systems, and because we've got large window-to-wall ratios and the glass isn't very good, and the client didn't want to put exterior insulation, and they're not going to do anything about infiltration, this is going to be a really crappy building, and so we're going to have to step up our game, and we're going to have to put in a little bit more different systems than we would do if the building actually had a lot of passive solutions, right? So it is not the Holy Grail. It is, in fact, the cleanup crew, and I think it's important that we understand our role in this whole process. The tools, and we're going to start talking about tools now, so I hope we understand that when we have, when we're sitting down with our clients, that we have these dialogues about the filtering systems, the lenses, what's in the standard, the clothing, met rate, air temperature, radiant temperature, humidity, air velocity, stratification, all of these terms, those are our lenses, those are our factors. And we can use that, and we can sit down with our clients, and now we can have real honest dialogues about the design intent for these buildings. And then what we can do, and this is one of the exciting things that we did at Spring Camp, we're going to talk about this later on, is we can sit down with some of the design tools. And so if you have a phone handy or a second computer, if you want to search CBE thermal comfort tool, by all means do that, because what we're going to do now is we're going to spend the next while going through this tool. So I'll give you guys a second to locate that if you want. And as we go through the tool, feel free to play around with it. And all you need to do is just listen to my narrative, because we're going to describe the tool and how powerful it is. So the first thing going back is that recognize who we designing it for. That's really important, and understand that there's diversity in spaces with people, and so we should also recognize that. So this is what the screen looks like. When you go online, you're going to come across the screen, and if you're on a phone, you're going to have a little bit different screen than if you're on a computer. When you're on the PC or the Mac, whatever, you're going to see the full enchilada right there on your screen. If it's a phone, you're going to have to scroll through to get the different screens. And this is really sort of where we do the inputs and the outputs, and it tells us whether our combination of these factors are going to be in compliant with ASHRAE 55 or not. There's the phone version for you. For those of you that are following along, you can just scroll and you'll be able to see all the different screens. So there's a bunch of switches that we can use. And the first thing we want to do when we get onto the tool is we want to switch it from being a psychometric chart, just air temperature only, just to air temp. And then there's another switch which takes us over on the left-hand side. You can see that switch, the operative temperature. We want to click that, because ultimately what we want the screen to look like is this, where we can put in a value for air temperature and where we can put in a value for the mean radiant. For those of our audience today, Gord, they're in the US, they're probably looking at this going, it's in Celsius, what am I going to do? They're all panicking, I don't understand the units. It's okay, because you can switch back and forth between IP and SI. And the message you should see here is don't worry so much about the units, because you'll see what we want you to understand is the relationship when you change the values. That's the power here, and to see whether you're in compliance or not. So now we're sitting there with a tool that says, okay, well, what is the air temperature and what is the mean radiant? And these are the inputs that we have. And for the most part, all of these are pretty easy to wrap your head around. Air temperature, as we mentioned, it's not what's at the thermostat, it's actually around the person. So now we have to say, well, how do we determine that? And say, well, if it's fairly good construction, when I say fairly good construction, for those of us that are in IP units, it might be like, say, 20 BTUs per hour per square foot. Something like that is okay construction. It's not great. It doesn't really suck. And we're not getting into the 30s or the 40s, and we're not down to passive house. We're down to 5 or 8 BTU hours. But for the most part, in good construction, you can assume that the air temperature around the person is going to be very similar to what you set on the thermostat. But if it's a crappy building, then you're going to have to make some judgment calls or use more advanced software. And we'll talk about that later on. The mean radiant temperature is something you can actually calculate, and it's not that difficult. In fact, Gord, we spent time with Tracy and Alexis and some other people from Building Knowledge showing them how to do that calculation, and it's actually quite simple. The airspeed, again, is around the person, and I have to tell you, I've not been in a building where the airspeed became a problem unless someone was actually standing over top of the registers or underneath the diffuser. For the most part, the airspeed is pretty good. If you get into tricky geometries, tricky architecture, then again, we should use a little bit more advanced software tools to establish that. But I would say for the most part, air velocity is not normally a problem in the wintertime or the summertime unless someone is standing right over top of something. The relative humidity, again, is something that you're going to control, so you would put in the values there. If you're not going to control it, then you're going to want to play around with the tool and find out where the pain thresholds are. So ramp that up to 70 or 80%, take it down to 20%, just see what the consequences are. Maybe through that exercise, you might decide that you want to control humidity. The MET rate and the clothing values are inputs, and those are all selected items off a table, and we're going to come to that. And now, anyways, when you get all of these right, when you get the combination right, you're going to be in compliant with the standards. So, as I mentioned,
Robert, it is true. The mean radiant temperature, as you mentioned, is it's a calculation that you do separately, and our folks did it, and we found it daunting if you're going to try to do every room in the house, but when you helped us quickly identify and we'll use the term rogue zones, then it's that simplified it, but it did take some calculations and understanding of building science. It's the place where the work of an energy advisor makes a lot of sense because they're doing a lot of the same calculations anyway and inputs. So it's a good place, it's a good person role, energy advisor, to do the mean radiant temperature calculations.
Absolutely. And you bring up that term rogue zone, which is something I coined, I don't even know when, Gord, but I just remember doing design work and looking at drawings and going, okay, that's not looking like the other zones, and that's going to be a problem. So it's those zones that and you know them intuitively. If you've done design work for any length of time, you can look at a set of drawings, look at how that building's going to be oriented on the property, and you're going to go, uh-oh, like that's gonna bite us in the butt if we don't actually pay some attention to what's going on in that space. So rogue zones are important. So here we have an example where we're actually putting in the code required 72 degrees. So again, we talked about in the phase one, part one of this, building codes don't represent comfort. There's a requirement to hold a set point, but there's nothing in the standards that say we have to have this value. So we put it in here just to see what happens, 72 degrees. But the mean rain temperature, we've dropped it. So this could be a building that's, under design conditions, and the enclosure is not terrible. Like, we're not talking 50 degrees here or 60 degrees, but it's close to 70. But because of the other combinations of the humidity and what the people are doing, met rate's low, clothing's low, that there's a good probability here that many people would not find this space to be comfortable. So you can switch back and forth. So if you want to work in IP units or SI, and you can just see that the results are the same. And so let's go a little bit further into the tool. We'll talk about some of the menu items. PMV, we talked about that earlier. Part one, predicted mean vote. Get everything right that we can do some reasonable projections about whether people will be uncomfortable or not. So that's important. We can switch that between that or the adaptive model. We can define whether the people have control over their airspeed or not. And this is really important. We know that when people are restricted, like they don't have access to change their environment, they can't add a fan, they can't open the windows, they can't change their clothing because of clothing policy, that actually has a psychological effect. It actually makes it even more difficult for them to enjoy the space. We can change how we look at humidity, whether you want to do wet bulb, dew point, however you want to look at it, you can change that on the screen. And then the two most important factors, or two more key points, are that what are people doing, because that has a huge effect, and then also what are they wearing. So metabolic rate and clothing, and then you can do a number of things here. You can actually create your own ensemble. So if it's not in the menu item, you can actually build up your own, which is very useful if you're from a different part of the world and maybe you have different clothing cultures. Then you can actually do these things, and you can say, okay, well, here's the clothing value of what we wear in our world. And then for those in other parts of the world, say, well, we wear this, right? So we can do that. And then we can also use what's called the dynamic predictive. We know from research that's been done is that when people get up in the morning and they ask Alexa, what's the weather forecast for today? Or Siri, or whoever it is that you're asking, that they'll adjust their clothing for the day if they know what's going to happen. And so you can use that tool as well. One of the additions that was added to the program many, many years ago now is this solar calculator. And what the solar calculator does is it allows us to take a room and we can put windows in it, and we can just say, okay, well, here's the performance of the window, here's the exposure to sunlight, and here's where the person is in that beam, if you will. And so what are the consequences? And so you can do an adjustment to the MRT based on shortwave radiation, which is an incredibly powerful tool, as we found in some of the exercises that we were working on. So that's sort of if you want, the meat and potatoes of the tool. And then we look at this predicted mean vote, we look at local discomfort factors, and the tool has a whole set of menus that you can punch in numbers, looking at things like radiant asymmetry. These we've already talked about these. Drafts, angle drafts, vertical temperature gradients, these types of things, all the way through to floor surface temperature. So these are either inputs that you can do through calculation or through judgment call, or when you get into challenging architecture, you can actually model them with other types of tools. And I would just suggest here that when you're using these tools, for the most part, when you get basic geometry, basic architecture, you're not going to have a problem. It's when you get into the origami, flamboyant architecture that you really need to sort of, recruit somebody that knows what they're doing with other more sort of advanced software. But for basic stuff, you're going to be fine. So one of the local factors, several of the local factors that we're showing here has this term radiant asymmetry. That's when you got temperatures on either side of you that are extremes. And the New Yorker just published here recently in March. This was the front cover. If you're not familiar with the magazine, it's a very popular magazine. And tackling the New York experience in apartments. I mean, it's a cliche. Gord, I think what they call it, that the double hung thermostat in apartments in New York. They're all running on steam. Everybody is hot. The only way to control it is by opening and closing the window. We have floor temperatures that we need to concern ourselves with. We have stratification, the difference between the ankles and the head. And then we also have drafts. And I just want you to observe this. It's like Poltergeist was in my hotel room. You can see the pillows fluttering. And so as soon as I saw that, I said, Gord would like to see that picture. So took a video of it. Drafts like that, if the room is hot and the air is cool, they do provide some sensation, but you would never want to have that, during the wintertime. Drafts aren't necessarily a good thing. So we pay attention to these issues. So going back to the tool, let's just set up some parameters. We're going to go with the building code requirement, 72 degrees. We've got a mean rating to 78, which means we've got a building with probably some glass, probably some thermal bridging going on, probably exposed to a south-southwest exposure for those of us here in Canada. You can see what the airspeed is, the relative humidity, met rate, clothing, we're all good. And in this case, with this combination, we're going to be in compliant with the standard. But what happens if we start to change the parameters? So here we've gone from 74, 72, but look at the mean radiant temperature. We've really jumped it up. So what does that tell us? It tells us that we probably got a really aggressive window to wall ratio. The glass probably not the best performance. Airspeed, relative humidity, and the clothing. So we've changed these parameters, and now that program is going to tell us, hey, you may want to pay attention to this stuff because most people wouldn't find this space, comfortable. And so one of the things that I want you to appreciate as we're going through this is that we're actually fixing the problems before the building gets built. And that is so important. We don't want to come in after the fact to try and solve comfort problems when we can do it ahead of time. And that's the value of this whole exercise that we're doing. So how do we compensate, for a space that's got aggressive radiant temperatures? Well, we can bump up the airspeed. We can put in a ceiling fan, and that can help us compensate for this thermal experience that may not otherwise be comfortable. So,
Robert, can I
yeah,
take you back? I just looking at the top there where the bar says complies, doesn't comply. Just explain for a second and remind folks the PMV and the PPD, because
sure.
numbers are changing, and I think that's useful to highlight to give you a sense of what that means.
Yeah, so in part one, we talked about the predicted mean vote and the percentage of people dissatisfied. And this was a result of the work that people like Ola Fanger did many, many years ago. And they basically, through research work, established that when you have all of the cookies in the jar all done right, everything, all the ingredients are done right, that we can predict that most people will experience the space with a positive attitude. But if we start to get things wrong, they're going to start to complain. And the more things you get wrong, the higher the percentage of people that will be dissatisfied, which is on the right. So this target that we have is 0 plus or minus 0.5. That's what we're shooting for.
On the
Okay?
PMV. On the
PMV. That's exactly right. And is it perfect? No, what we want to get the value of the PMV is it's identifying the landmines. That's, it's basically like, your sergeant, and he's taking you through, you're the brand new soldier in the field. This guy's got all kinds of scars and wounds, and he's guiding you through the field. Well, that's what this tool is. It's your ability to look at the architecture, the enclosure, interior systems, mechanical, and say, okay, where are the landmines? And that PMV is going to keep you on the safe track. If you can get 0 plus or minus 0.5, there's a good probability you're on the right path. Okay, so that's what that's all about.
Thank you.
Yep. All right, so let's play around. Let's just say maybe we're not going to do humidity control, and there's a high probability that it could start to climb up. So now we're starting to get some fairly aggressive humidity. We don't know of any argument that you wouldn't want it that high, like that's getting up there. We'd like to see it down lower than that. So let's talk about humidity. What we know is that when you are sort of in the normal range of indoor conditions, humidity just isn't sort of going to be an issue for us, provided that we're controlling it. But where it becomes a problem is when the conditions start to get up into the more aggressive areas. And then the body starts to switch from doing cooling via radiation and convection and starts to look for using evaporation, that latent process of removing heat through sweating and evaporation. And if we don't provide a place in the room for that moisture to go from our bodies, in other words, it gets suppressed because the humidity is high, you're going to start to overheat. And so what we want to be aware of is that when we get into these aggressive climates, or we have bad architecture that leaks a lot and that moisture starts to migrate into the space, or we're over ventilating our space and we're not taking care of the moisture, is that we're going to start to see aggressive conditions. And in these cases, we want to pay attention to that in our design process. So that's on the thermal comfort side, but there's a whole bunch of other reasons why we control humidity. And I'm not going to go through the whole list here, but you can see that. And that good design practice looks at all of these things. These are the reasons why we control humidity. And I just want to put in a plug here because I was raised on radiant heating and cooling with dedicated outdoor air systems. That was my very first, biscuit when I was a little kid. That's what I chewed on. And people get all twisted out of shape. Oh, you can't use radiant cooling, it's going to condense. Well, no. If you're a competent designer, you're going to control moisture for these reasons. And because you control moisture for these reasons, condensation isn't the issue that we think it's going to be. But by the way, that applies to air-based systems too, right? So controlling moisture is important for many, many reasons besides the thermal comfort part of it. All right.
Was a quick question I'll just answer. Chavez was asking relative humanity. Oh, I guess maybe he's saying there's a typo there. Relative humidity, I think, is what we were chatting about. I don't know if there was a typo on yours or not, but I guess he's joking at us. Sorry.
Was I can't remember. Yeah, maybe it was humanity. I'll go back and look at it later.
Yeah, exactly.
All right. There is a red flag that when you're looking at design, you have to, when you're doing an assessment of your representative occupant, you're saying, okay, what are they going to be wearing and what are they going to be doing? And if there are times where that person is going to be doing a low MET rate, so they're reading, for example, and they're going to be wearing really light clothing, so summer shorts, t-shirt, maybe sandals, flip-flops, that type of stuff, then you're going to want to have to do the local assessment. That's really important. I would say probably 80, no, maybe more, maybe like 70% of people that actually do thermal compliance checks with ASHRAE 55, most of them get the first two personal factors, clothing and MET rate, and they understand the other four general factors, but they always miss the local factors. And it's right in the standard. When people are doing low MET rate, low clothing, you got to look at those local factors. So floor temperature, stratification, radiant symmetry, all of these things are important. So we can put those values in. And what I'm showing you here, these X values, means that we've exceeded the tolerances. So we know we don't want to have too high temperature difference between the walls and across a person or the ceilings. We know draft can be a problem in the wintertime, not so much in the summertime. Draft can be a good thing in the summertime, especially if it's beer, comes in a glass, frosted, right? Draft, that's the best, right? Ankle draft, temperature gradient, all of these things come into play. And then this solar calculator. So what I want to do is I want to demonstrate the power of this tool. So going back to an example where we've got, air temperature, and it's quite common, people will assume that the surface temperatures in the room are represented by what's on the thermostat, which is a bad mistake to make. But let's just see what happens here. Okay, so we've made this mistake that the MRT is the same as the drywall, and I can tell you that rarely ever happens. But here we're going to set it up, and then we're going to say, well, okay, let's just see where we go with this solar calculator. So we open up the menu and we start to populate it, and we can tell, okay, well, is the person standing or are they sitting in front of the window? There's the air temperature. There's the mean radiant temperature that we assumed was going to be the same. We can look at the altitude above horizon. So all of these terms, by the way, are the definitions and are all explained in the tool, by the way. So how much of that energy is coming on the glass? Here's 700 watts per meter squared. What the transmittance of that glass is. And this is very much similar to the solar heat gain coefficient, but not quite. But there's some clarity on that. But for this purpose, let's assume how much of that energy is coming through the glass, how much of the sky vault of the whole solar thing, how much, I don't know if you can see this, is actually coming through. And then what percentage of it is actually hitting on the body, right? So here we're saying about 50%. And there's guidance in the tool that says, well, is somebody at a desk? Are they sitting in a chair? Are they standing up? All of these are provided. And then what the shortwave absorptivity is. And so most skin, clothing, wall surfaces have fairly high absorptivity, what we call the solar or the thermal optical properties of anything really. And our bodies are actually almost perfect absorbers and emitters, which is why we talked about in part one how we're almost the perfect radiant element. Anyways, you can populate this and then you can do the calculation. And so what I want you to observe is that we assume that the MRT was 74, and then we say, well, let's take a look at what the consequences are if we put glass in there. And so you do an adjustment of that, and you can see now the MRT is not the same as the air temperature anymore. Now it's 92 degrees, and now we're no longer compliant. So in the past, before you participated in the seminar, because I know this happens all over the world in all kinds of design offices, making the assumption that surface temperature is the same in the air, it's not, and that you need to evaluate the impact of shortwave radiation coming through glass. And you can see that it can take something that you thought was compliant, and now, it's not. And if you don't solve that problem now, Gord and I will be here today to witness and testify that it will come up later. So when do you want to do it? At design stage or after the people have moved in and now they're on the phone giving you, you know what, because it's uncomfortable in the space, right? You never want the call, right? You always want to be able to solve problems up front. All right, so then there's this adaptive method, and we talked about adaptive, and I'm a fan of adaptive processes, but we want to make sure that we use it properly. And there's a way to take the tool, and you can switch between the PMV method or the adaptive method. Those are two methods that we use. And you can again populate the cells, the menus, if you will, and it'll tell you whether you're going to be in compliant with the adaptive methods and change the airspeed, change all of these things. And as long as you're sort of in that zone, then you're good to go. And so we call it hybrid systems or multi-purpose systems. And so that's fine. Now, what I want to point out is that as you familiarize yourself with this tool, there's lots of documentation online. There's YouTube videos explain how to do all of these things. But there's some things that I would recommend that as you explore it and learn about it, that reach out to Building Knowledge Canada, because they've got some people that are now trained on it. And you're going to come across situations where you're going to go, you know what, we're just getting out of our league, and let's bring in some people that know a little bit more about it. One of the cool things about the tool that I really like, particularly from a design point of view, when we were doing design working with clients, is we could create different scenarios, and we could bring these scenarios to the architect and the client and point out, well, because you did this, here are the consequences. And if you would consider doing this, here are the consequences. And if you would really sort of take everything we have to say to heart, here are the consequences. And so we tried to take the client from sort of a good, better, best, or worst, all the way through to, look, if you really fix these problems, you're going to have an awesome inside spaces from a thermal point of view. So it allows you to do that. I think it's one of the most powerful parts of the tool myself. All right. We mentioned elevated airspeeds, and I have to tell you, like, this is a project that we're like 99% finished. Gord, you know what that's like. At some point, I don't even know, at what percentage of a building are you done where you just say, you know what, we're done? Is it 95 or 99? Anyways, we've taken this old farmhouse. We actually don't know when it was built because it was brought to the site, and then over its life, it had several therapists. They did all kinds of, as we ripped it down, we found 5 different forms of insulation. We found bare wires. It was quite an experience. and have completely rechanged this building, the experience. And one of the things that we knew from calculations is that not probably maybe, I think, I'm trying to remember the numbers, like maybe 40 hours, 60 hours a year, something like that, that we were going to need the ceiling fan. So we put the ceiling fan in there. There's no mechanical cooling in here, although that is under debate right now, whether we'll do that or not. But for the most part, we've taken a really conservative building that's, or well, I don't know how to use it. Not just say there wasn't a lot of thought in the original building to insulation and tightening it up. We actually did use air barrier in here. And I got to tell you that we reduced the leakage, Gord, by, I think it was 67 or 70%. Massive, massive, massive change.
Amazing.
And that, yeah, it's a great product. We've, and we weren't, when we did the test, like the before and after, we actually weren't done. We hadn't put in the new windows yet. We hadn't finished the flooring. So I'm thinking that, we're probably, when it's all said and done, because we'll have the crew back in, within our crew, and we're probably going to be probably somewhere in like the 2.4 ACH 50. That's from like 9.8, right? I'm good with that. That's for me. I'm good. We can take that building. That building now got another whole life ahead of it, right? So, anyways, the tool. There's another part of the CBE, the Center for the Built Environment. They have this ceiling fan tool, and you can put in ceiling fans. You can model the number of fans, the type of the fans, and then you can see the cooling consequences or the perception of cooling that people have. It'll tell you what the effect is. And you can see, if you take example number one, that table, you can see which solution to display. See example G on the very top row. Look at that cooling effect. This is, people perceive the space to be 9 degrees cooler than it actually is because of the elevated airspeed. So it's a hugely powerful tool. Why would you not use ceiling fans rather than going to more mechanical refrigeration, which we're already getting hammered on, right? Talking about COPs and the type of refrigerant and the more equipment that's on net. I mean, there's a whole argument, to be using ceiling fans over more mechanical refrigeration. Anyways, I love the tool. When I was practicing, we used it all the time to try to convince clients. Some of the clients just told us to go pound sand. They hated ceiling fans, right? You're going to have those clients. They don't want to hear about window to wall ratios. They don't want to hear about performance. They don't want to see ceiling fans, right? So then
It's
you
always
got
the challenge, Robert. It's always the challenge. And it's an easier conversation at the beginning than at the end.
totally, yeah.
This is the challenge I have when I go in and say, well, you could do a ceiling fan. Are you kidding me? I just spent $1.5 million on this. Now you telling me again? Why didn't you tell me that before?
Yeah, exactly. So we also know we want to be careful with ceiling fans because there are some conditions where we call the operative temperature, which we talked about earlier, part one, it's the marriage of the mean radiant with the dry bulb. When that starts to get up, as does the humidity, that ceiling fans can provide some relief, but at some point they won't provide any relief. And in fact, they can actually be harmful to the occupants. And so we want to make sure that when we're using ceiling fans, that we're using it within, and you can get pretty aggressive to be able to use ceiling fans. But if somebody is elderly, for example, or they have maybe it's a thyroid cancer or something that affects their regulation, their thermal regulation in their body, you want to be really careful about that. That's why when we talked earlier about know your client, like who are you designing for, right? And so we don't want to make assumptions that could actually end up leading to problems. We want to make sure about that. All right. Can we teach this to the housing industry? Absolutely. I got to tell you, so we're going to tell the story again, Gord. I'm going to tell this till the day I die. I'll probably tell it on my deathbed. So Gord and his crew, Tracy and Alexis, spring camp, called up and said, okay, Robert, we want to do this workshop. We want to take all of our guests, 180 people from the representatives from the building industry, so architects, engineers, contractors, manufacturers, the whole gamut, and we want to expose them to this whole experience that you've been talking about for the last however many decades. And then I was thrilled about it. I got to tell you, Gord, I was a little nervous, a few anxious nights. But I think, what did Tex tell you? He said, if you're going to do workshops, make them short, make them simple. And we did that. And, for everybody that's online listening, and Gord will test this, and same thing, the other folks with Building Knowledge are online, that it was a huge success. Getting people to sit down with a set of drawings, break up into teams, just like an integrated design team, and look at the building through a lens of somebody who's doing a thermal comfort assessment, and then trying to find those landmines and those rogue zones. And then, okay, well, yeah, there's going to be a problem. So how are we going to solve it? So yeah, absolutely, we can teach industry how to do it. Here's the example that we used at Spring Camp. It was a multi-level building, all kinds of different geometries, cantilevered sections. We had large floor-to-ceiling heights in some of the rooms, like the great room, for example. We had, yeah, it was just had all of the things that when I look at a building like this back in the day when I was doing design, and I would look at this and I would look at the property and I go, well, okay, we've got a large great room here, tall ceilings, all glass. Right there, that's a rogue zone, right? It's gonna get flagged. And then we look, at the bedroom. It had a cantilevered floor section. The bathroom itself had two exterior walls, exposed ceiling, exposed floors. Right there you're going to have an issue. Same thing with the primary bedroom. It was over top of a garage, so that becomes have to start paying attention to that. Three exterior walls, exposed ceiling. So you start looking at that, and so this is one of the things that Gord, I was glad when I retired is that I stepped on a lot of landmines, as all of us do that have a lot of experience, right? This gray hair came about. I'm actually only 40 years old. I've only been in the industry. That's what the industry does to you. Right? But you learn this stuff and be grateful for those learning experiences because it teaches you to look at a set of drawings and understand people in spaces. And then you can say, okay, well, I'm your guide here. That's my job. My job is to guide you through making decisions so that when you start to live in this home, that you're going to be able to extract the maximum amount of enjoyment and you don't have to be stressed out because of downdrafts or overheating or bad humidity or and that applies also to things like air quality, right? Odors and all of this stuff, right? So this was the building.
And I will add one other comment, which was the basement in today's world is almost a de facto rogue zone, right? We didn't used to expect much out of basements. We wouldn't spend much
Yeah.
time down there in and out of it to do storage. Well, now when we're using basements, lower living areas, and we're putting secondary suites, boy, that's the quintessential rogue zone. It's cold surfaces, it's cold floors, it's no natural light, all those things. So almost all houses now in Canada, any new houses with the expectation of that lower living area, it too becomes a rogue zone. So we're not necessarily going to talk about it today, but I want to remind folks of that.
Yeah, exactly. So Trace and Alexis put this drawing out there and said, okay, here's what we want everybody to do. So they broke everybody up into these teams, became the integrated design team. And they said, okay, well, let's look at these drawings and let's identify those rogue zones and let's talk about it. Let's talk about how people would sense these environments they're in and what would their perception be and anything else that might affect their comfort. And then the second thing was to come back later and say, okay, what are the options that we have available to us to solve these potential problems? And it was really, it was one of the best exercises ever because we had people thinking about the geometry and we had people thinking about mechanical solutions and building science solutions, insulation. How can we, reduce the bridging? And then also think in terms of cost. Well, what are the consequences of these? And we had a couple of builders in the room that said, you know what? Sometimes the cost of fixing the problem up front is way less money than trying to fix it on the back end, right? So when Doug Terry was in the room and some other builders were in the room, and they just brought a wealth of knowledge to the dialogue. It was just awesome. Like I said, I'm buzzing about what happened there. And so one of the risks, and I'm just going to show you some of the risks that were identified in the exercise. The living space was for sure a challenge. We had all of these massive windows, elevated ceilings relative to what was in the dining room. So you had this change in elevation. And of course, depending on how you oriented, and you can see here it was oriented west, but that, as you change how that's placed on the property, that's going to affect what's going on in the inside space. We looked at the bedroom, again, high exposure area to cold. Again, we talked about that earlier on. But that's what your eye is looking for when you're looking at these drawings. You're saying, okay, well, how is this building situated on the property? Well, this is on the north side. And then let's think about the enclosure and let's think about infiltration and the window to wall ratio and the performances. And when you start to realize that you've got spaces here where it'd be really difficult, for example, to condition the ensuite here, given that it's got an exposed floor because it's cantilevered, it's got two exterior walls plus a roof and a small floor plate area, and people are going to be in there naked and wet, right? So, for those of you that are online, maybe from Egypt, you may not appreciate it, but gets to minus 40 degrees C here. Like it's it's cold, and you don't want to create these environments, but paying attention here. So, and then as Gore pointed out, the basement and so what we started to look at, well, how do we solve these problems? And Tracy and Alexis took us through some of the solutions. One of them was looking at the high window to wall ratio. If we put in performance characteristic A, whatever that glass was, and we got non-compliance based on the tool that we use, how can we bring that space back into compliance by changing the glass? And so they messed around with the solar heat gain coefficient, dropped it down to 0.25, and all of a sudden, okay, well, now we're starting to think about how people are going to experience, and we can change their experience by changing the solar heat gain coefficient on the glazing systems.
And I think it's important to note that the first one showed 19% of the population might experience discomfort. Now we're down to 6%. Many of the builders on this call will say, well, I must always be building for the 6% because everybody always complains. So it's not perfect at 6%. It's a prediction tool, right? So keep that in mind.
Yeah.
And I've had some success helping clients with that. I get it. This house was designed we didn't know who was going to buy it. You've now purchased it. We designed it for less than 10% of the population. You fall outside that 10%. Let's get to work and see what we can do for you, because you have a sense of comfort that's different than what we had to design for. I remember saying to a client, I've said it many times, picky people have to pay more, right? You're a particular person. You are quite sensitive to these things. And my experience is we got to find a different solution for you because of your particulars. So sometimes that works, sometimes it gets the matter, but I feel like I just need to be honest and say, you have particular needs. Let's see if we can match your needs to a solution.
Yeah. And I hope everybody online appreciates that this whole exercise is about drawing people into the world of the client, getting it to see it from their perspective, have empathy for how they will live in those spaces, and then appreciate that you're given an opportunity during the design stage to manipulate those building characteristics. And that when you start to see the relationship between people and the spaces that we're designing, and then be able to create the proper conditions by manipulating those values, that is, you know what, Gord, if that's all we ever achieved in these two parts, that's a win.
I agree.
Right? So
I agree.
Yeah, so that's so my concluding thoughts of this, because we're getting towards the end, we want to make sure there's time for questions. And I call it the romance of industry language, because the industry has used language that is very romantic, but basically it's lies. And so one of the ones is people saying they can make a room comfortable. And my first question to that is, how do you know? Have you ever asked a room if it's comfortable? And if it actually answered to you, you might want to do an exorcism. Right? Rooms have no feedback mechanism. And we know thermostats aren't it, because they're just sensing themselves. So we can't make rooms comfortable. There's no way for us to actually ask the room how it's doing, right? How are you feeling today, right? Or would you like it warmer? Would you like it cooler? If somebody actually saw you having a conversation with your room, you're probably going to be in a hospital somewhere wearing a white coat. I'm just saying. Right? So let's be careful of this romantic language that we like to think makes it simple. I can make your room comfortable. Yeah, unless you can figure out a way to get feedback from the room. I just say cautious on that term. The other one is making people comfortable. You can't make somebody feel something that they don't. And and to me, in fact, if you could, it would actually be evil. Like, you feel this way. Well, I'm going to make you feel somewhere else. And we talked about this in the first part, where Andy Oding at spring camp asked the room, How many people are uncomfortable? I think, Gord, you said it was between 30 and 40%, right? So does that mean we made 30 to or 60% of the people comfortable, but the other 40% we didn't? So if you're going to make someone comfortable, then that's a 100% requirement. Well, we know you can't make everybody happy. So making people comfortable, yeah, also sits on that's a romantic thing to think about, but we can't actually do it. Um, Delivered comfort. We see this all the time. We're going to deliver comfort. Like you're going to buy our particular heat pump or, unit, whatever it is, and we're going to deliver it to you like it's like a menu item. Well, can you return it if it doesn't deliver? I don't know. You can't deliver thermal comfort. It's a subjective feeling. People own the experience. It doesn't come in a box. It doesn't come in a zippy device. It's their personal experience and it exists up here based on what you've done around them. So let's be careful about using terms like making rooms comfortable and making people comfortable and delivering comfort like you're a server at a restaurant. And we can't fix bad architecture with zippy stuff. If you have bad architecture, you have a problem regardless of what kind of technology. You can throw all kinds of technology at the solution. If the architecture sucks, the enclosure sucks, interior systems suck, I can tell you, you can do all kinds of things to try to fix it. The problem isn't the technology, it's not the equipment, it's the architecture. And it's aggressive window-to-wall ratios. It's not recognizing dominant patterns, solar patterns, wind patterns, moisture problems, all of these things. There's nothing you're going to do about it. And that happens also in hot climates, right? So let's make sure that we understand that you can throw all kinds of technology at problems, but until you fix the basic stuff, good luck, right? And then the other thing is, we talked about this earlier on in terms of load calculations and HVAC design being comfort design. It's really romantic to think that you're sitting in an office, Gord, doing load calculations, sizing ducts, picking heat pumps. If you're on the hydronic side, picking boilers, going floor heat and blah, blah, blah. And everybody's going to be huddled around, what you're designing and load calcs, and everybody's going to be happy. Yeah. That's a Hallmark card. That one there, right?
Yeah.
Just isn't going to happen, right? This process is for compliance with the building code, and the thermostat serves as a witness that you've actually done your job, but it's not requirement in thermal comfort. We have other things to worry about in thermal comfort. And that goes back to this concept, because here in Canada, for those that are from Egypt or India or the UK, wherever, we have a requirement here. Thou shalt maintain 22 degrees C in all living spaces at design conditions. And we know that there's lots of places where 22 degrees C is on the wall, but everybody in the room is either too hot, too cold, too muggy, whatever the complaint is. So be careful of that. So at the end of the day, Gord, for everybody online, at the end of the day, and you actually mentioned it in the first slide, what we can do as an industry is we can use these combination of factors. And that means that we have to pull everybody in. We have to pull in the architect, the enclosure design person, the interior people, the HV people, and we can create these conditions, these thermal conditions, which would reduce the probability that people will have this perception of discomfort. That's all we can do at the end of the day. And the more we understand our client by asking them, who are we designing for? And when the more we know about architecture and enclosures and interior systems, and when we match the problem with the right mechanical system, then we've done our job. We've reduced the probability that people are going to complain. And that's all you can do. Can't make them comfortable, can't make the room comfortable. Load calculations is not designed. 22 degrees is not a proxy for thermal comfort. All we can do is create the conditions. That's it, Gord.
That's wonderful. And we do have some questions, and we're a bit of the rapid round, but I will take a stab at some of these questions. There's two that are very similar. Thermal comfort subjective, but there's metabolic rates that are different. People have different needs. How do we satisfy that? Angela said, who do we use as the surrogate, if you will, as the proxy? And you might say, well, the elderly, the sick, maybe you would give them priority, or you would give them adaptability. And in my case, my three sons each had different, I would say, comfort needs. And it took me 10 years to basically figure that out, to say you should be like the others, and then realize, no, that's not going to happen. We spent another 5 years fiddling with the central mechanical system to see if I could figure that out. And the last 2 years of his high school career, I put in a ceiling fan. And what it meant is that he had control, one of the sons had control over his sense of comfort. And just the fact that he had control made all the difference.
Yeah.
And it was in his room and in the family room. And yes, they fought a little bit in the family room as to who got to, sorry, not the family room in the cottage. They spent a little bit of time fiddling over that as to who has control of the con, if you will. But that's what you do, is you start thinking about those kinds of things. Morteza asks, what's the best practical way to find the mean radiant temperature? Can you use a thermal camera? What about new construction design? We know we did the calculations. You can do it knowing the thermal characteristics of the wall, knowing what's happening outside. You can do a mean radiant calculation. It is a calculation. Robert, is it legitimate to use in an existing structure to use a thermal camera and actually get the temperature of that wall? Is that practical?
Yeah, you can do a weighted average reading, so with the thermal camera, or do the same thing, a weighted average calculation. So if you're doing an existing building, what I would do is I would take my thermographic camera and I would do it quadrants on each of the surfaces. So I do upper left, upper right, bottom left, bottom right, and I would do an average of that. And then I would do that for all of the other 5 surfaces in the room, and then I would average all of that out. So just when you're using your thermographic camera, you just have to remember that the emissivity off of glass is going to be a lot different than if it's off drywall, right? So either put a piece of tape, on the glass, shoot that piece of tape so that you're getting not a low emissivity reading, but actually the actual emissivity off the surface. So, and let that tape acclimatize to the temperature of the glass.
Great, thank you. And then Tiger was asking, what's the plus minus accuracy? Well, the CBE tool is, again, a predictive tool. It's not perfect. And more importantly is we know it's not going to satisfy everybody. That's the key. You would say to your client, 10% of clients are going to find this to be acceptable. Does that sound like you? Do you want to go further? And how slightly warm, how slightly cool do you want to feel? So it's a predictive tool that could be adjusted based on your client's needs. Celia asked a couple of questions about air tightness and insulation levels. There might be some concerns there. I think, just to reiterate, we always want building enclosures to be airtight. We want buildings to be ventilated, and that could be by opening windows or that could be by mechanical ventilation. But let's not confuse air leakage of buildings as being a desirable thing. No, air leakage, unwanted air leakage, is never desirable. What we want is control over the air leakage and then controlled ventilation. Hopefully that answers that one, Cecilia.
Yeah. Gord, I would just add on to that leakage in buildings creates or contributes to stack effect, depending on the building, right? So if you, in terms of drafts, right, that we don't want to have drafts in buildings, particularly in the summertime, it's fine, but in the wintertime, we don't want that. So in terms of ventilation, air quality, and then also thermal comfort, we're solving many problems by having a building that's tight. And as Gord pointed out, the ventilation side, but also reducing stratification through stack effect. This whole concept of, what did people say? They want the building to breathe? No, we want people to breathe. The building we want to control.
Right. Pradeep asked mentioned that it's a great tool, and then he noted the limitations when you have a production builder using the same model of house in different orientation. Absolutely, this is the challenge, and that's where we would say responsible architecture to recognize that and to call that out and say, boy, this house might work really well facing east-west, but it's going to be a challenge north-south. So if we want to avoid, don't sell that model on that site. But it's definitely pretty, that's a big concern. Mohammed had I would say, a more sophisticated question around ASHRAE Standard 62, which is the ventilation standard, and then how it would change for hospitals and the other restrictions in different areas. So he's asking about the CB tool and other analysis. Well, remember, 62 is about ventilation and air quality. This is a comfort tool, which would impact ventilation, how it moves around the building, but you'd have to use both of those tools, I guess, is what you would suggest. David's asking about recommended for seniors' houses for air quality and comfort. Again, David, I think you've got the sense. You would use the CB tool and you would say, I'm going to put in different clothing rates, different activity rates, and understand that those folks are different. And we could go to a more complex analysis of what those folks are with. And then again, David's asking about health issues with respect to outdoor air. Again, this session's been more on indoor comfort, air quality we've addressed in other sessions, but this is a great topic, David, for another webinar series, another session that we'll do on. So what do we do when the outdoor air quality is bad? How are we going to manage wildfires? So I'll leave that one for a second webinar or another idea. Robert, I'll get you to stop sharing and I'll share just quickly as we finish up. Oops, sorry. Finish up here. I'll just share. Thank you.
Go. Yeah.
So some really good questions, which I appreciate. And then I'm going to share my screen, which will be this one here. Sorry. And hopefully folks can see that. And I'll just say, in terms of summary and next steps, and you kind of added it up nicely, Robert, I really loved your challenge of stop using the words or the phrases that we've been using and understand that there are designs that are possible. They're comfort design tools. And I would say at Building Knowledge, we're happy to help with that. Alexis, Tracy, and others have been trained. If we can help you, that'd be great. Hopefully you heard it's not necessarily the whole house that you have to deal with. It's the rogue zones or maybe rogue orientations. We highlighted that big windows and small spaces are a challenge, but there are strategies and great window partners that can help with that, the Geldwins of the world, for example. And then understanding the science of heat flow, conduction, convection, radiation. And Robert, you made a really nice case of match your solutions. If it's a radiant problem, match it with radiant systems. We did a study for Upinor years ago on radiant cooling and determined that if you had good humidity control, good dehumidification, you could do radiant cooling in just about every climate zone. Maybe not Houston, that might be a bit of a push, but in most climate zones, you could do radiant cooling strategies. Now, whether you can get enough cooling density to offset the cooling load associated with those big panes of glass, that's maybe a different story. But I just want to thank Robert, and I just asked everybody online to give Robert a big round of applause, if you wouldn't mind. Really appreciate that.
My pleasure.
What a wonderful sense of creating a whole new conversation for us. So thank you very much, Robert. And then I just remind you to stay tuned for upcoming webinars. The only two that we have booked solid at the moment are October 29th and November 19th. Already out of this session, we now have a couple of more topics that we may want to add. There will be more later coming later this summer. But I would say to all of you, have a wonderful summer. Thank you, as always, for joining. Thank you so much to the sponsors, Enbridge and Casey, for helping us with this webinar. We just love seeing the same familiar faces or names on the screen. Really appreciate you folks signing in. I know this one brought you a value. I don't have to ask because there's nothing more valuable than spending 3 hours with Robert Beam. But thank you, Robert, again. Really,
My pleasure. Thank you, everybody. Appreciate it.
Thank you all.